Hi everyone! In this video we're going to do another set of counting problems. The problems we're focusing on in this video are about permutations of a subset of elements, which means you're only rearranging some of the elements that are possible, or when some of the elements are identical, like that second example that's on the screen right now. Hooligan has two O's, and those O's are the same. It doesn't matter which O you put first, they're both O's. So we're going to use permutations and factorials throughout these problems and see if we can figure out the exact question that we're being asked. And that's really the hard part about these problems, generally speaking, is working through the question very carefully and deliberately and making sure we're exactly answering the question that is being asked. Because just small changes in wording can completely change the calculation. So this first one, determine the number of possible arrangements of 4 letters from the letters in riposte. So whenever you've got one of these word problems where you need to rearrange the letters, I like to double check that there's only one of each letter, even if you're pretty sure. Riposte, S, T, and E. Just going through the process of writing out each letter and making sure that there's only one of each will catch a lot of mistakes. I've seen many students, and myself included, who make the mistake of not noticing when there's repeated letters. So it's worth taking the time to just make sure that there's no repeated letters. In this case, there are not. Which means that there are 7 letters total, and we are trying to arrange 4 of them, which is the permute button on your calculator, which is the same as doing 7 times 6 times 5 times 4. But 7p4 is a lot quicker. Let's do this hooligan question. So determine the number of possible arrangements of the letters in hooligan. Well, hooligan has double O. So there's H, O, there's 2 of them. L, there's 1. I, there's 1. G, there's 1. A, there's 1. And N, there's 1. So there's a total of 8 letters. And there's 2 O's. So if it was just 8 different letters, then it would be 8 factorial. 8 factorial possible arrangements. And the only thing that the 2 O's adds is that we don't care the order that the 2 O's are picked, right? If you pick the first O and then the second O, it shouldn't be counted differently from picking the second O before the first O. They're both just O's, and we don't care which one's which. And so the correct answer is 8 factorial divided by 2 factorial. And sorry, I forgot to say at the start, but as with my last video, I'm not actually going to pull out the calculator for these. The point is coming up with the calculations. You can do the calculator step on your own if you like. Here's a trickier one, harebrained. So let's go through carefully. H, there's 1, A, 1, R, 1, E, 1, B, 1, R we already have. So H, A, R, E, B, R, A, I, N, E again, and D. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, this should be a... So there's 11 letters, is that right? Let's just double count. There's my cursor. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we had 11 ticks. Okay, also a good idea to double check that, right, to make sure that you didn't count something incorrectly. So 11 letters and 3 doubles, right? So there's 3 letters that repeat doubles. So that is 11 factorial divided by 2 factorial, 2 factorial, 2 factorial. And I just realized I didn't have an example with a triple letter, but let's say it was like a creeper from Minecraft. C-R-E-E-P-E-R. So we've got 2 R's. We have 1, 2, 3 E's, and then 2 other letters. Okay, so that's a total of 1, 2, 3, 4, 5, 6. So that's 7 factorial letters divided by 2 factorial for the R's and 3 factorial for the E's. Okay, cool. So that's how you do problems like that. Okay, let's move on to another set of problems, which is sitting students together in a class. So this first one's just straight up. You've got 7 students. They need to sit together in a row. How many possible arrangements of students are there? Well, there's 7 students. Students are all different. So it's just 7 factorial. 7 choices, 6 choices, 5 choices, and so on. Okay. What about, same problem, we've got 10 students that must sit together in a row, but we have 2 different groups of friends who want to sit together. one set of 3 friends, and another set of 4 friends. Okay, so basically you need to sort of think about this way. We've got students 1, 2, and 3 have no friends, I guess. We've got one set of 3 friends, and then we've got another set of 4 friends, and those are your 10 possibilities. Now, the way that I like to think of these is I like to think of these sort of like as being in a bag together, right? So there's like a bag of all of the X's and a bag of all of the Y's. Those 2 groups of friends are going to sit together. And so when we're placing our friend groups and our non-friends, we have a total of 5 different things to place, right? We've got the 3 friends, 1, 2, 3, plus we've got these 3 count as one object because we're going to place them all together, and these 4 count as one object because we're going to place them all together. So that first set is basically 5 factorial. Then what we imagine doing is sort of like looking inside of this bag with the 3 friends. How many different ways can the 3 friends sit together is 3 factorial. And then the 4 friends, there are 4 factorial ways they can sit together. So it's 5 factorial times 3 factorial times 4 factorial. Okay. Now let's do this one. Same idea, but now we've got 2 troublemakers, and these 2 must not sit together. How many different arrangements of students are possible? So 7 students, but 2 troublemakers must not sit together. Now, figuring out the number of ways that 2 students cannot sit together is actually a fairly hard. Well, I mean, it's not too hard. You can use triangular numbers to solve it. If you know what triangular numbers are, that's a hint for how you could do this directly. But there's an easier way. The easier way is instead of like figuring out how they don't sit together, what we're going to do is we're going to do all options. So all possible arrangements of the 7 students minus, like take away, the ones that we don't want. We don't want them sitting together. The trouble, let's call them the TMs. TMs sitting together. And then that's how we can solve this directly. So all possibilities for 7 students is just 7 factorial. Now the 2 students sitting together means you've got like a bag of the 2 troublemakers plus 5 other students is a total of 6 factorial options for how you're going to arrange the pair of troublemakers plus the 5 other students. So 6 factorial. Then the troublemakers themselves, there's 2 factorial or just 2 arrangements. Okay, and so those are 3 types of, sitting together or sitting apart questions. Let's do some textbook questions, which is basically the same thing again. Just slightly different context. So Mr. Armstrong is arranging textbooks on a shelf. So all 3 questions start with that. I've got 6 math books, 2 science books, and 3 English books. Okay, so that's a total of 11 books. How many different ways can Mr. Armstrong arrange the books if all of the textbooks from each subject are different from each other? Well, if they're all different from each other, then this is just 11 books. So that's just 11 factorial. All right, plug 11 factorial into a calculator. Whatever it is the answer. Okay, same setup, different number of books. So 6 math, 3 science, 2 English, sure. But how many ways can I arrange the books if all of the textbooks from each subject are the same as each other? So we've got 6 math 30 books, grade 12 math books. We've got 3 physics books, and we've got 2, Shakespeare books. So how many different ways can we arrange those? Well, again, we've got a total of 11 books. So it's 11 factorial, but we're going to divide by our 6 math books. There's 6 factorial ways of arranging. Our 3 science books, there's 3 factorial ways of arranging. And our 2 English books, there are 2 factorial ways of arranging. And so it's 11 factorial over 6 factorial, 3 factorial, 2 factorial. Cool. Let's do one more. So Mr. Armstrong is arranging books. Okay, same thing. 12 books this time. Okay, but whatever. But how many different ways can Mr. Armstrong arrange the books if all of the textbooks from each subject are different from each other, but he wants all of the math books together? Okay, this is like the friends sitting together thing, right? So inside the bag, we have our 7 math books, plus we've got 3 science books, plus we've got 2 English books, is a total of 6 objects that we're going to arrange, 6 factorial. and then the 7 math books we need to rearrange. So it's 6 factorial ways of arranging the 3 science books, 2 English books, and all the math books, times 7 factorial for the ways you can arrange the 7 math books.